Technology. It makes us think of numbers, data, analytics, and math.
Good afternoon, my dear friends. Welcome back to post-lunch session of 34th International Conference on VLSI Design and 20th International Conference on Embedded Systems. What an amazing show today during the first half. We have excellent speaker coming in and sharing their views. We are to talk with Ravi from Intel, Professor Daly from Stanford, Mr. Paul from Cadence, and Dr. V.K. Saraswat from Niti Aayog. So here I'm back, and I'll quickly share the little feedback which we have received during last one and a half hours during the lunch break. That people are glad, they need not to take a taxi in the morning, or they need not to worry about what kind of weather it would be if they're traveling intercities. Everyone is enjoying the conference from comfort of their homes or their work offices. So I would like to take this opportunity to thank to our all volunteer team who work day and night to get us to this live show. So without any further delay, I would like to call on our distinguished speaker, the inaugural speaker of post-lunch session. Next slide, please. So this is a quick glimpse of all of our speakers on 5 days. So we are now on day 1 post-lunch first session. Next slide, please. So without any further delay, I know you are eagerly waiting out to hear back from Anand. I would like to welcome Mr. Anand Ramorti, Managing Director, India for Micron Technologies. And he'll be sharing his view on memories at the heart of intelligent system. And he heads the Micron team, who are world leaders into the memory. So we'll get started with this session with the exciting background about Micron through a video, and post that Anand will continue with his talk. Welcome, Anand, on the stage.
Thank you.
Technology. It makes us think of numbers, data, analytics, and math. All the stuff that goes on in our head. But the truth is, the head is powerless when it's not fueled by the heart. And memory is the heart of technology, the driving force that pumps life into every product, application, and innovation it touches. Memory is the heart of science, allowing researchers to explore the microscopic detail of the human body and the infinite grandness of the universe. Memory is the heart of industry, making precision agriculture more productive, vehicles more autonomous, and smart homes more convenient. It is the heart of consumer experiences, making esports more active and VR more interactive. And it is the heart of AI, enabling it to do everything from make us coffee to make us laugh. At Micron, accelerating intelligence is more than a science. It's a passion, which is why we've assembled more than 37,000 thinkers and doers in over 18 countries who know that innovative memory solutions are essential to our future. A promise to continue pushing the limits, shaping the way we live, the way we work, the way we see the world. Memory is at the heart of what makes the impossible possible. And we are the memory makers. Micron, intelligence accelerated.
Over to you, sir.
I get goosebumps every time I see this video, partly because I'm very proud of Micron's legacy of innovation. but also because memory is such a fundamental part and piece of the traditional network storage compute paradigm. And let me start with a quick data. In the last 10 years, if you look at the entire shipments of semiconductor devices, this is memory, non-memory, logic, put them all together, 80% of devices shipped were actually memory devices. That tells you how much, be it every device, every experience, every inference, memory is truly at the heart of every intelligent system. Good afternoon, everyone. I am Anand Ramorti. I am MD for Micron India. And it is an absolute privilege to be part of the VLSI 2021 conference. As Preet rightly said, I am the session after lunch, so I hope I can wake you up with all the progress we've been doing in the space of memory and storage. This may be a quick personal introduction. I've been in the semiconductor domain for a little over 2 decades. My first 10 plus years were actually spent in the US. I started my career as a GPS engineer. GPS then, in the late 90s, was still a technology restricted to avionics, defense, and then it was making its useful transition to the mobile world. So I started designing front-end analog down-converter chips to begin my career in the Bay Area. And then over time, I moved to the more logic world, building controllers, SoC chips for infotainment, telematics, embedded, industrial, and other applications. And also had a couple of P&L stints running profit and loss for business units at semiconductor majors. That teaches you how to build a roadmap, drive innovation. Also, more importantly and more practically, telling you how to sell what you build. I have been lucky enough to be on both sides of the fence. When I was in the US, I helped run development centers in India. And now being a part of the India Development Center, I understand the dynamics of working across the globe and making things happen. Very glad to be at Micron, and I completely feel home at Micron. Talking of Micron, so I'm assuming most of you are familiar with Micron. It's clearly, next slide, please. Micron is a leader in the semiconductor industry. We have been in business for over 4 decades now. In fact, this is not the slide I was looking for, but that's okay. I can talk to Micron, and then we'll come to this one. So Micron is a 4-decade plus legacy in memory and storage. It's the 4th largest semiconductor company with $21 billion plus of revenue, 13 manufacturing sites, 17 plus countries, 44,000 patents issued to date, which is mind-boggling because if you think of it that way, it's roughly 1,000 patents every single year. So clearly a company led by innovation and disruptive innovation at that. We are leaders in many of the technologies, essentially a strong, comprehensive portfolio of solutions, NAND, DRAM, and a lot of the emerging categories in between. And I'll be talking more about some of our innovation and how it adds up to what we are trying to do in this new data-led world. I'll stick to the slide first. Now, you cannot have, the previous slide, please. You cannot have a presentation, a keynote without talking about this new data-led world. This is a new data-led economy, and it is so pervasive. We can't think of a sector or a vertical that has not seen the surge of data, be that be mobility, automotive, healthcare, media, industrial, agriculture, you name it. Data is everywhere. And what has happened? The good part is there is a surge of data. The not so good part is everything that needs to kind of grow in proportion to data has not happened. We'll talk about compute, we'll talk about memory and storage, we'll talk about all the different building blocks that have not been able to keep in pace with the non-linear eclectic growth that we have seen on the data side. And this is and when you talk of data, you cannot but not talk of memory, because at the end of the day, data is memory. And I just want to pick a couple of examples to kind of drive home this point a little bit more. Now think of automotive. I spent many years in automotive. Automotive is making that very useful transition in the last decade from what was more like a horsepower-led vertical to what is more like a brain power-led vertical. If you go inside a car, look at the number of controllers, you look at the number of memory nodes, look at the number of sensors, these have been growing exponentially, which also means that I have to make a lot of decisions and compute at the edge level, at the device level. And that transition is happening as we speak with huge implications for memory and storage. The other example that I need to think of, the 5G era. The era is on us. Some parts of the world are ahead. But as 5G is not just about mobile broadband, that's clearly the salient part of the 5G revolution. It is also about machine-to-machine communication. And it has huge implications for the kind of memory capacity, the kind of inference time you need, both at the edge level as well as at the cloud level. But the one example that I would love to share with you, and for those of you whose love for physics is similar to mine, I'm sure many of you are aware of CERN. CERN is the Center for Particle Research in Europe. This is where the Higgs boson particle was discovered. Now, if you go to the largest collider, just to give you some sense of the power of compute and data, in that collider, which does particle detection, there are close to 1 billion collisions every second. 1 billion collisions a second, generating 1 petabyte of data per second. In fact, this generation of data is so overwhelming, we don't really have a mechanism to actually capture the data or even make any sense of it. So what they do there is actually they kind of filter it, and they crunch it in the data center. And after they crunch it to the data center, they do some level of data reconstruction. They filter, and then they try to bring it to a more manageable status. And that just tells you that we are seeing what I call the 3 V's of data movement. There is obviously velocity, there is volume, and there's variety. With all the 3 V's, it's not just about a blind improvement in compute and storage, but also very smart improvement in compute and storage mechanisms. Next slide, please. So we talked about data, and obviously as this surge in data is happening, you see the slide on the left where it talks about the kind of data consumption. This is not news to all of us. What you see listed on the right are the 6 critical, I call macro challenges that we are seeing in this data-led economy. I'll pick on a few of them to give you a little more commentary and color. The stagnation in general purpose computing. I come from the compute background, and I can tell you that computing is still in most part very processor driven. Up until a decade back, we looked at data as one data. We did not know how to parse data based on the origin and the need of making some inference out of it. So our computing historically has been very, very processor driven, not data driven, not memory driven. Of course, what has happened also in the last decade, people realized this issue, and we have this new era of very focused compute accelerators, which are based on workloads, based on the kind of problem you're trying to solve. You have accelerators, you have very, very differentiated co-processors, but they're still processor centric. You're still talking about processor. You're not talking about data, and that's the challenge. And there are different approaches that I'll be talking about later in my presentation about the trend in that direction. There is a little more focus on distribution of compute across the entire value chain, but it's still early days. We're still not close to data. We are not processing fast enough. We're not processing quick enough, and we are still a little further away from where data is coming and residing. That's one challenge we have. The other challenge, and it's a very significant challenge, is on the memory side. If memory is not able to keep pace with compute, all the advantages of compute are kind of basically lost. This is something I'll touch in much more detail in the coming slides, so we'll kind of pause on it for a bit. The other macro challenge is on the energy side. On the energy side, there is obviously a macro challenge. As I said, the data, with more data is more energy consumption, but the source of energy in our globe has actually not kept in pace with the needs. That's more on the macro side. But even at a microchip level, if you look at it, right, a lot of the energy is lost in the distribution of data. If you look at a typical chip, you would find the actual compute function is probably 5 to 10%. The rest of it is largely used up in movement of data and processing and management of data, and which is something we are not being very efficient about. So clearly, energy is a constraint that we have to start talking about more and more. Also, while we're talking about AI and ML, the data set training can happen in the cloud, but we have to figure out a lot of the inferences are going to be drawn at the edge, and we need to figure out what is the right approach of compute and storage mix at the edge to make sure that you're not actually clinging onto the cloud or to your data center for making those decisions, consuming more power and introducing latency in decision making. So clearly something that we need to work on collectively as an industry. The security landscape, this bothers us quite a bit because The interesting thing here is as data grows, so does the vulnerability. In fact, so much so that it's almost looking like a perfect storm. Right? You have so much data, every device that enters the ecosystem at any part of the value chain is actually introducing more and more vulnerabilities. In our DRAM world, all of you must be very familiar with the rowhammer exploit, which has been in for a while. And what we're finding is this exploit has actually gained a lot more momentum as the memory density has increased. The more memory density, the more cells you have, the ability to go and flip rows of in a typical DRAM cell has actually grown up. DRAM array has actually grown up. So it's clearly almost sounds counterintuitive. We're becoming more and more vulnerable. In fact, I heard one of my good friends say that hackers these days are actually leveraging physics a lot more than just software. And clearly a cause for concern as to how do we actually manage this holistically, not just at the device level, but from device all the way to cloud. Because when you talk of security, it's always about defense in depth. You can make your chip secure, you can make your memory cell secure, but if you're not securing the entire cloud device data path, then you're obviously not doing the whole job. What we're also finding is shortage of people. We talk about all these new trends in AI and ML. We don't have enough people trained in AI and ML models. We don't have enough people trained on cybersecurity. And just think of it this way, the example I love to quote, the time it takes to go and actually manually check out an MRI or a radiogram or an X-ray versus being able to train someone to go and do it. It's a matter of such a big improvement in terms of productivity and time. In fact, it's so exciting that I'd love to quote that we are actually doing a small project with IIT Delhi as we speak, where the context of COVID, if I have an X-ray, if I have a COVID X-ray, and it looks very similar to a person who may have had pneumonia, the pneumonia data set is very comprehensive, is very well understood. The COVID data set is minimal. So you train your data set with respect to traditional X-rays coming from lung infections and use the right algorithm to figure out who is more likely. Instead of going and doing expensive tests, you can almost predict who's more likely to be having COVID. So that clearly people is an issue. And the more counterintuitive part here is as more data comes in, the decision time, the time it takes to go and make a decision is actually shrinking. Because in many areas like medical health or financial business transactions, it's all about time. And every second is lost, you have millions of dollars. So it is quite a complex landscape. We have challenges. And next slide, please. Now, of course, these are macro compute challenges. And we can go to the next slide, please. Now, of course, when I talked about memory being such an important part of the whole network storage and compute paradigm. Now, look at the graph. This is what would overwhelm most technologists. Can also motivate some, depending on who you talk to. Now, when you look at this chart, what it tells you is we're always looking for more performance. We want more bandwidth because bandwidth in terms of memory bus, in terms of data transfer, we're looking for faster refresh and access cycles. Then, of course, there is a cost involved in scaling technologies, be that be a logic or memory. There is material and equipment cost. There is power consumption that needs to come down. So this is clearly a very overwhelming chart. And what we're doing at Micron and what's happening in other vendors, what I have below are the three prominent pillars of memory technology today. And we will start peeling the onion one at a time. Let's start with DRAM, right? Now, DRAM is mature. DRAM has been in vogue for over 4 decades now. And it started, the scaling challenges have been known for a while. The scaling kind of stopped some many years back. And because, when you think of DRAM, you can, in fact, the gap between DRAM scaling and the compute scaling, that gap has been widening in the last couple of years. So this is a perfect challenge. So much so that at 10 nanometer, where we have kind of hit a roadblock in terms of physics, we have new nomenclature, and Micron, and other memory companies. We talk of 1X, 1Y, 1Z. In fact, we just released our most advanced 1 alpha node for DRAM. So clearly, a different nomenclature to show that you're making progress at a certain node, but not able to clearly break the barrier in a more conventional way. Talking of DRAM, right? What is a DRAM cell? A typical DRAM cell, as you all know very well, it still follows the 1T, 1C model. You have a transistor, you have a capacitor. It's a charge device. There's a charge inside a capacitor. Now, the most intuitive way of scaling is I want to shrink the cell. Scaling is all about Moore's law. I'm going to shrink it. But as you shrink, you're reducing the volume at a planar level. You reduce the volume, you're actually impairing the capacity. So the next intuitive thing to do is to increase the depth of the DRAM. But as you introduce depth, you have challenges related to charge leakages. You also have some charge collection, which means capacity is impacted. So net, the traditional way of scaling, both in terms of XYZ axis, is not possible with the DRAM. So what we're doing at Micron is looking at different types. We're looking at non-planar transistors. We're looking at 3D capacitors and making sure we are looking at newer materials, which is going to be so critical. And it's going to be a very strong collaboration between, it's a multifunction collaboration, starting from technology development, manufacturing, design, quality, you name it. And what is also going to be very critical in DRAM scaling is having the ability to actually model, because as you want to model the newer nodes, you want to start, and you don't need a lot. What you need is essentially the ability to look at process, the ability to look at transistor designs, and in fact, I'm very happy to let you know that a lot of that modeling work actually happens out of Micron India. At Micron India, we make sure that we're able to assist our teams globally to be able to predict and forecast what kind of advancements would be needed to make DRAMs faster and quicker. So that's the DRAM scaling challenge, but it looks like there are some paths, some approaches, some workarounds to go and make sure that we can still keep adding capacity at a reasonable price point. Moving on to NAND. So thankfully, the NAND scaling challenges are a little more, the NAND challenge is a little more easier, with, I would not say relatively easier, because in the NAND cell, you have the ability to do a little bit of planar scaling in the XY axis. Thanks to some innovation in technology, the 3D NAND revolution happened a few years back. Many vendors are shipping in enough volume, and you can do a lot of vertical stacking. And also in the NAND world, we've been able to do a lot of logic scaling, which means start with the single bits, you're moving to multi-bits. Multi-bits means more states, which means more quicker access. But there is obviously an impact in terms of performance. You always have to do the trade-off between SLC, MLC, TLC, QLC NAND. But the good story is the paradigm that people love to use is essentially a staircase model, right? So what do you have when you have limited real estate footprint? You start building a tower on top of it. But as you start building the tower, the cost of infrastructure also goes up. And the cost of building the 100th floor of a tower is going to be much higher than the cost of building the 10th floor. So again, through a combination of innovations, at least at Micron, we just announced our 176-layer 3D NAND. So you're adding more layers. You're doing some innovation in circuitry. You're making sure that the objective is not just to keep on stacking, but making sure you get the right kind of performance in terms of access and speeds, so that it's not fully compromised. And the third category is obviously the new era of storage class memory devices, 3D crosspoint, that most of you are quite familiar with. And this is where we're trying to kind of bridge the gap between the NAND and the DRAM world. And I'll talk a little more to it in my next slide. Next slide, please. Next slide, please. Yeah, this is again, I talked about when I started my career, there were so many standalone devices. I remember seeing a lot of standalone NOR flash, SRAM memory chips, and other flavors. Of course, many of them have kind of perished as standalone options. You see a lot of SRAM and NOR in embedded memory on a chip. But today, it's largely the NAND and the DRAM, right? DRAM for performance, but it comes at a cost, and NAND for scale, but it's expensive. And all the research that's happening is to find the holy grail where I can get something which is a perfect match between the NAND and the DRAM. 3D crosspoint to some extent gets there. But you have to understand that even though the approaches are there, the fundamental laws of physics apply the same way. And you can't change it too much, right? You cannot basically have speed and retention both happening at the same time. You cannot have the fastest speeds and the highest retention, because the famous memory wall comes into the picture and messes up the whole story. So if you look at the research in terms of, I would categorize the research for new memory, the new emerging memory, into broadly two buckets. At one level, we're looking at trying to find out what would be the right atomic approach, which is trying to manipulate at an atomic level. You start manipulating an atom, playing with the atoms, and seeing how you can create a new set of memories. The other approach, the other bucket, is more about the electron spin itself, spin up, spin down, which applies more to the magnetic storage class of devices. And both of them have pros and cons. There are actually so many approaches and proposals out there. It's hard to kind of keep track of all of them. But you have to, one thing I want to highlight, and it's kind of obvious, but it's important to know, it's not just about finding the right class of memory. You may even find something which has a beautiful trade-off between performance, cost, bandwidth, but then it should be manufacturable. It should be something that can be reliable over a period of time, and it should be able to yield significantly over a period of time. And that's the holy grail that we will probably never be able to crack, but that is the part that inspires memory researchers to go and make those things happen. So next slide, please. So I have talked about, and this is just an animation telling you that we are trying to shift left. We want to get to a point where NAND becomes cheaper and cheaper. And we're also trying to see if DRAM can also scale down in terms of cost without impacting the performance or reliability. Next slide, please. So, we're reaching an interesting point in the presentation. So if you're just doing a quick recall, right, we talked about the macro challenges. We talked about the challenges that exist in the memory world, especially the DRAM world and the NAND world. But what we often do at a systemic level, we don't have to solve every single problem at a device or a component level. Obviously, smart people start looking at a systemic level. To give you an example, if you look at a traditional DRAM cell, not all DRAM cells are made the same way, right? And if you're doing refresh, you don't have to go and refresh at the same rate with every single cell, because some cells are different from the rest. So this is, there's a concept of, online profiling. You can start profiling at a system software level as to which cells do I refresh and which do I refresh at what frequency. That leads to improvement in power efficiency. It also leads to improvement in not having to go and fix every single problem at the device level. So clearly, there's a lot happening in terms of, I talked about the processor memory interconnects, the memory processor bandwidth is getting better. We're talking about CXL. We're talking about PCIe. The intent behind all these innovations is to make sure that if I have computed and I have had enough cycles of compute, I am able to, in proportion, be able to transfer the data and make sure that I get the right outcomes, the right decisions. So clearly, there's a lot happening at a systemic level. In this slide, I want to give you two very unique examples. On the left, you see a kind of an innovation happening in terms of how you stack a solution, right? Multi-chip packaging has been in vogue for a very long time, where you are able to stack memory and processors together in a simple package. Very useful for applications which are real estate constrained, like mobiles and some parts of automotive. But clearly, other markets don't have a real estate constraint. But it depends on which application you are kind of targeting. On the left, you see our HBM2E, which is a high bandwidth memory technology from Micron, where we are able to actually enable a very significant improvement in the system bandwidth. And that is happening because we have a series of DRAM dies stacked up on top of a processor. And because of all the innovation we've had in the silicon via technology, we're able to ensure that these are mechanically stable and they're reliable, and they can give you that high throughput that you can get by essentially keeping the memory very close to the processing unit and keeping it in such a way that you don't put pressure on the die or the silicon beneath it. That's one good example of system bandwidth improvement happening at the cloud side of the equation. On the right side, we have an interesting example where we just announced our GDDR6X standalone graphics technology device. And this is more on the edge side, where by using a new, not a new technology, PAM4 has been used in the networking domain, but by using the PAM4 multi-level signaling advantages in terms of data transfer, we've been able to transfer data much faster. Almost, look at the previous generation and look at what we are able to do with the 6X innovation. So two different examples, one at the cloud level, one at the edge level, but by using system bandwidth smartly, either in terms of data transfer or in terms of packaging, we're able to ensure that we can derive outcomes without, and kind of have a workaround the memory challenges, the memory wall challenges that I talked about in my previous slide. Okay, next slide, please. So it's not all hell and gloom, right? It's clearly the traditional memory hierarchy is still relevant. We have SSDs, we have DRAMs, we have NAND flash, we still have hard disk drives in many parts of the business verticals. They're still delivering and performing, and vendors, including Micron, have figured out unique approaches built on strong innovation and multi-discipline collaboration to make sure that they at least have a couple of years of innovation left. We still see a couple of nodes ahead of us where we can go and meet some of the needs and demands of this new data economy. I talked about persistent memory, this whole concept of storage class memory coming in, which tend to kind of take advantage of merits of the NAND DRAM worlds and provide something in between. I gave you an example of high bandwidth memory. We're trying to focus on the bandwidth part, the constraint of the memory constraint. Computational storage has been in vogue in the SSD world for long, where we have smart controllers sitting in conjunction with NAND dies and making sure that you get the right kind of performance with the right access speeds. We could see a little more of intelligent controllers coming in the DRAM side of the equation. We haven't seen that evolution happen as fast as we would want it to happen. And then the two most important innovations happening as we speak, and these are difficult, but the direction, the trajectory is all set, is to have more and more of in-memory computing, or called analog compute. And what it says, there are so many functions that actually don't have to go to your processor for help. Many of these functions, it could be a simple copy. It could be many of these functions can be done in memory, and the memory cell, we got to start leveraging the compute, make it sit close and close to the memory part of the subsystem. And by doing so, we should be able to get a lot of edge impact. Since a lot of data is moving to edge, a lot of these edge-based inferences can happen much faster. Some of the research is actually very, very positive. And of course, I'm a little bit of a romantic when it comes to innovation. We've been talking about how can we be more like the human brain, right? The human brain has been the most fascinating part of our memory and compute journey. Of course, neuromorphic computing has been in discussion mode for many decades now. We haven't gotten there yet, but the beauty of it is, I think there are enough efforts. We look at our traditional compute model. It is very deterministic, right? It's clock-based. It is very, very orderly. Whereas the brain is very, it can handle a lot of abstract. It's quick, it's fast, it's very abstract, and it doesn't consume a lot of power. An average human consumes less than 20 watt of power. So obviously a lot of research happening to figure out how can we start using a lot of those, and we have to completely relearn how we do compute as we move to more and more concepts around the neuromorphic computing. And it will also be very specific in terms of application. It will be more in the area of robotics, in the area of AI as an edge. But the story or the thought I want to leave you with is the industry, and Micron in particular, we've been figuring out very active approaches, workarounds to handle the traditional constraints of memory computing. And we have enough independent technologies that may take a little bit of time. These technologies may sometimes take almost a decade to come back to fruition, but the path, the roadmap is laid out, and we will be leveraging them at the right time for the right applications. Wonderful. The last slide, please. So thank you everyone. Just wanted to come by and tell you a little about what we're doing at Micron, and also a little bit about what's happening at Micron India, because a lot of what I said, a lot of the functions and actions are happening in Micron India. So, but as we keep our focus on innovation at Micron, and I'm sure at all the semiconductor vendors, we cannot lose sight that eventually what we're all aiming and rooting for is to have a world which is more fair, more equitable, and more sustainable. Thank you again for your time, and thank you for the opportunity.
Thanks, Anand, for such a insightful talk. And as since morning session, the queue of question is more than the given time. So in the interest of time, I'll pick up one combined question which came in different pieces, and this is something even was talked about this morning, that the most of the data, the 90% of the data generated is in last couple of years, and most of it, 80% of this data, whole generated data, is still unstructured data. So at Micron, is there any plans beyond giving the memories? Is there any plan to to provide a top-up post-processing on and beyond the data, which could be more value add to user, because now users are not looking for data. The consumers of data earlier used to get Excel sheets. That's how we started. And now we digitalize this whole, and the data is so humongous that they have their own challenges. We have the focus companies who are only doing this data processing. But do you foresee something of that sort of coming immediately, not only from Micron but in general from the industry side?
Good question. Good question, Preet. In fact, this is on the radar screen, and in fact, we have very specific data accelerators and inference engines that we are developing at the edge side, right? Because many of our markets that we deal with, be that be mobile, be that be automotive, they need quicker data. They need good parsing and filtering. And the data, as you rightly said, is not very structured. But we have a few approaches in mind in terms of very focused decision accelerators and inference engines that we're building. And they will be co-located with our memory, so that that's the beauty, right? You keep it closer to memory, you add some good algorithmic structure to it, and you start seeing some. And this is still a few years away, but we actually made a few acquisitions in this domain the last couple of years. So I'm very hopeful this is going to see a lot more traction in the coming days.
Okay, excellent. Thank you. So in the interest of time, I see all our panelists are already on the call. So we'll close this call with a big thanks to Anand for his insightful talk. Because memory is at the heart, as you said, and everyone is looking forward to the what next in the memory domain. So thanks a lot for your time. And on behalf of this conference and the VLSI Society of India, we'll be shipping a physical token of appreciation to you, but kindly accept our virtual thanks to you. Thank you.
Thank you very much. Thank you, everyone. Have a good evening. Good show. Bye now.
Okay. So with this, let us move to I would say the most excited part of the day. Okay, and we knowingly kept it towards the later part of the second part of the second half of this day. Because a lot of people are curious about the title of this particular panel discussion, decoding semiconductor landscape of 2030. So there's little change in the program. Satya Gupta, who's president of VLSI Society of India and chairman of IESA, Indian Electronic and Semiconductor Association, he was supposed to moderate this particular panel. Unfortunately, there's a demise in his immediate family this noon, so he has to step out. So he would be not able to make it for this panel discussion. So as to bring up the flow further, I'll be moderating this panel discussion. I hope it's fine with all the panelists. Thomas, Dr. Raj Kumar, Dr. Dinesh. So with your due permission, we'll get started with this panel. I'm sure I can't replace Satya, the kind of vision, the deep thought he has with 30 years of experience, but I would try to justify my presence here for the interactive discussion with you all. So let me take this opportunity to introduce each one of you. So I'll start with no particular order. So let me introduce Dr. Thomas. Dr. Thomas, he's Chief Scientist and Vice President at CEA-Lati. Though most of the panelists here don't need any particular introduction, but let me briefly introduce each one of you. So he received his electronics engineering degree and PhD from National Polytechnic Institute, France. From 1997 to 2000, he developed advanced SOI CMOS characterization, physical modeling, and circuit level performance evaluation with ST Microelectronics. Then he joined CEA-Lati, where he led different research projects with the industry, including ST Microelectronics, IBM, Freescale, NXP, and many startups. Dr. Ernst is author and co-author of about 180 plus technical papers. He's having 20 plus patents on his name. So welcome, Dr. Thomas, on the panel. Let me proceed further. I'm going, right to left this time. Let me introduce Dr. Raj Kumar. That's how I see all of you listed on my panel in this, virtual WebEx. So Dr. Raj Kumar, he's Vice President, Technology and R&D of Infineon Technology, based out of Malaysia. And he's heading front-end R&D unit and unit processing, development, product engineering, process integration, technology transfer, and conversion management, chip packaging, interaction, test technology, and innovation. So anything to everything related to the work which is done out of FEB, out of Infineon Malaysia. Raj has extensive experience in semiconductor industry, including establishing and volume ramp up of mega scale semiconductor wafer fabs across Asia and Europe. His technical expertise spans over a broad base of technology platforms, including smart power, power discrete, flash memories, MEMS, sensors, and logic technologies. So I guess nothing is left to be touched upon by Dr. Raj Kumar. So before joining Infineon in 2005, he worked at Semiconductor Laboratories. That time it was known as Semiconductor Complex Limited, back in India, Mohali, Chandigarh. And Dr. Raj Kumar, he's a senior member of IEEE and life member of Indian Vacuum Society. He holds doctorate degree in semiconductor process and modeling and a master's degree in electronics and science with majors in device physics and microelectronics. So welcome, Dr. Raj Kumar. Now let me introduce the gurus of most of us, Dr. Dinesh Sharma. As like the other two panelists, he even don't need any introduction, but let me briefly introduce him. So Professor Sharma, he obtained his PhD from Tata Institutes of Fundamental Research, University of Bombay. He was with Solid State Electronics Group of TIFR during 71 till 91. Other than the two intervals from 76 to 78, when he was visiting scientist at Leti. So he has a connect with the Leti back in 76 to 78. And then from 85 to 87, when he was with Microelectronics Center of North Carolina University at USA. He has been Electrical Engineering Department of IIT Bombay since 1991, where he is currently working as an adjunct faculty. So he has a deep experience, related to device modeling, technology development, over the 50 years, of his career. So with this brief introduction, I would welcome Dr. Dinesh Sharma on this panel. Dr. Dinesh, can you hear us?
Yeah, thank you.
Great. So let me, yes, sir.
Yeah, no, I'm happy that I shared my background with both Dr. Raj Kumar and Dr. Ernst. I was at Leti and I have had strong interaction with SEL.
Oh, great. Thank you, sir. Thanks for being part of this panel. So we have a lot of, I would say we have discussed a lot of connects to each other's organization. So with this, let me get started. So how we want to do this is we'll give 5 minutes to each panelist to put together their opening remarks, and then I'll start with a bunch of questions which we assembled through a lot of audience already, and post that we'll open the floor for the live questions and answers. So we can go in any order. So should we again get started from the rightmost side or leftmost side?
No,
Professor Sharma is the senior most, so let's start with that.
Okay. So Dr. Sharma, I will get started with your opening remarks, and then we'll gradually move to Dr. Raj Kumar and Dr. Thomas. So I would request admin to bring up the slides for Dr. Dinesh Sharma, the couple of files which he shared this morning.
Or shall I share from my side?
It's coming up. All yours, sir. Thank you.
Okay. So as you can see, I have very few slides, just 6. So first question is, as Preet had raised, what do we mean? Oh.
Yes, sir. Go ahead.
So yeah. So next slide, please. So to me, what is semiconductor landscape? That approaching 2030, if we look around the semiconductor electronics industry, what are we likely to see? and C in terms of technologies, device structures, design styles, circuit and architecture, and applications, and opportunities as well as roadblocks. So to me, that is what the title suggested, and that is how I have structured my presentation. Next slide, please. So let's look at these titles just a little bit. So let's look at technology and device structures. And the question is going to be, do we scale further or look for new horizons? In my view, not much headroom is left for device scaling. State-of-the-art devices are already at 7 nanometers or so. That means about, taking the lattice constant of silicon to be about 5 angstroms. This is 70 angstroms. So 14 atoms between source and drain. This is very, very small. Indeed, where do the source-drain regions end and the channel begins, so that we can even define the channel length in these terms? Clearly, the channel length has to be defined in other measurable techniques. The other part is that diminishing returns and exponential cost increases for seeking much shorter channel lengths. You want to go much smaller than this, even less than 14 atoms, then it doesn't come for free. So do we climb the mountain because it is there and keep scaling? Or look for other ways? Climbing the mountain could be quite costly. I'm sorry, I seem to have lost my connection. Yeah, okay. And anyway, the performance is limited by structures other than active transistors. The device on resistance versus... Just before the panel, we had a talk and many of these issues were discussed. The interconnect limitation and the leakage/tunneling for such short channel devices. Next slide. There are system issues as well. So there are power supplies issues. As the channels become shorter and shorter, we need lower voltages, and because we made the transistor smaller because we want more complex circuits, so the current keeps on going up. And efficient distribution of power is not a straightforward thing, and in the next decade, we need to see different solutions to this problem. One interesting problem is I/O protection. If the operating voltage itself keeps going down, how do you make protection devices which break down reliably at low voltages and within a very well-defined voltage range? The design window for I/O protection devices is shrinking very, very much. Also, that same issue of lower voltages, higher currents with shorter channels means there is a lower natural impedance. And in RF design, do we take leave of the 50 ohm standard? Matching to some standard like that is going to be increasingly difficult because the natural impedance will keep going down. But there are certain things which will remain. The antennas see the same space, and their impedance is not going to change just simply because we are scaling our semiconductor devices. So we will have to find solutions for this increasing gap between the natural impedance of our drivers and the final application. And how to run the systems at lower temperatures in spite of higher power density. The power density goes up, so the temperature will go up. On the other hand, the voltages are low, so and the leakages are already high. So how do we solve that conundrum? These are the systems issues that we will have to look at and solve over the next decade. Maybe we will look at application-specific technology development. For example, we would look at different solutions, not a catch-all solution, for power, for RF, for MEMS, and for sensors. We might even pause and say, has gallium nitride finally arrived? And provide solutions for this. Next slide. How about design styles? As technology and devices change and the applications change, the design style will have to keep up. Surely more error-tolerant designs with such complexity. Speed and accuracy trade-offs. We don't always need the additional speed offered by new devices. So we need to have, through design styles and circuit architectures, trade-offs between speed, which we see. Also, electrons and photons will not live. Electrons and photons will not live in separate houses anymore. Applications will require that the electronics and light will have to interact with each other. Mean, however, is that 3D technology will have to come into being, because personally, I don't see silicon as being a very efficient source of photonic devices. Demanded by other applications, what is the point of looking for doing photonics in silicon? We need to respond to the spectrum squeeze. We need more and more of spectrum, and it's very expensive. Therefore, we must use unused frequency ranges, and things like surface plasmonics and so on should come in this decade. And at every epoch of this technology, we have had this fork where one street goes towards higher performance and the other street goes towards lower cost. So how do we manage this fork in the next decade? And in particular, if we are scaling technology to such dramatic levels, how do we keep the costs lower? This is going to be a big challenge. So last slide, next one. I should not just be raising questions. So I'll go out on a limb and take a guess what will happen. So just like mobile applications have been the technology drivers for the previous decade, I feel that AI and machine learning may be the dominant application for driving new technology in the next decade. And new technologies will not replace the old ones completely. Many more levels of technologies will coexist, because for different kinds of applications, different levels of technologies will be optimum and appropriate.
Thank you, sir, for your opening remarks. Now I would like Dr. Raj Kumar to come and share his perspective.
Yeah, thanks, Preet. So I would say it's a pleasure, and more than pleasure, it's a great experience to share state with Thomas and Professor DK. So it's a pity that Dr. Gupta cannot join. So I also sent a couple of slides. So would you like to show?
Yes, it's on the screen now.
So I hope that everybody can see it. So can you go to the next slide, please? So since I'm using my company time, so before I go to the, let's say, future of semiconductor 10-year down the lane, I would like to share a little bit information about Infineon technologies. And of course, I mean, it is part of your life today and part of life tomorrow. And that's why it's fit very well into the topic of, let's say, future of semiconductors. So our mission is basically we make life easier, safer, and greener. And our vision is also very well fitting into VLSID theme, the cyber physical system. So we wanted to be the link between the real and digital world. Next slide, please. So unlike, that advanced logic and memories, only Infineon is focusing in a very big spectrum of technologies. So may I request you to go to the next slide, please? Yeah, so here you can see the sort of unique portfolio which Infineon offers to connect the digital and the real world. And we provide basically all the semiconductor solution between this domain. Next slide, please. So it seems to be a bit slow.
I would request admin to move to the next slide. Yeah, thank you.
Yeah. So in terms of Infineon position, so meanwhile, by acquisition of Cypress Semiconductor, we have made it into top 10 semiconductor companies. And of course, in power discrete and modules, we are very clearly number one, very far away from our next competitor. And of course, in microcontroller unit, we are standing at number 3. Next slide, please. However, Infineon focus is basically on mobility, energy efficiency, security, and Internet of Things and big data. And in these focus areas, Infineon holding basically the top position. And you can see on the slide, but Infineon is not only making the business, we are also very social responsible company. May I request you to go to the next slide, please. So, the semiconductor fabs conventionally use a lot of electricity, they use a lot of power. There are also a lot of specialty gases used, and with that, there is a carbon footprint. But we calculate that, on the one side, Infineon is a very energy efficient as compared to a lot of other fabs. So we have done benchmark. Our fabs use very less water, electricity, and create low emissions. But on that, top of that, whatever product we are producing, so mainly our focus, one of the focus is on energy efficiency, and then the carbon dioxide saving is roughly 40 times of what we are consuming. So with that, we are consistently making in the top world companies which are socially responsible. So this was a little bit about my company introduction, and let's now talk a little bit about what's, let's say, on the plate 10 years down the lane. So I think Professor Sharma has shown very well what's going to happen a little bit in, let's say, the advanced logic and memory space. So that is one part of the semiconductor. The focus of Infineon is mainly on, let's say, the niche market of the power semiconductor. And over here, we are not talking about, let's say, 0.5 volt and stuff like that, but rather we are talking about like 6,500 volt, and not a current which is in micro and milliamperes, but rather we are talking about hundreds of amperes. And then we are talking about the semiconductor basically which goes into arena of like power of 10 megawatt. And traditionally IGBTs and discrete MOSFET and even the diodes basically which are traditionally used. But now the new direction, also Professor Sharma mentioned about GAN, but GAN is making its way in let's say power before it goes to logic and others. So basically power silicon is serving very well, but when we look into the frequency, silicon is limited, especially when we talk about the power devices. IGBTs in the range of let's say few hundred kilohertz, and MOSFETs up to let's say 1 megahertz. But if you wanted to go beyond that, then gallium nitride is the clear candidate. And this is one of the, let's say, the focus research area for Infineon in power semiconductors. Not only Infineon, but also the company who are focusing in power. There's a very extensive research on that. And in fact, that international rectifier, which was acquired by Infineon in 2014-15, was the first one to launch the first semiconductor based upon GaN or GaN-based power switch in the market. And now, let's say, silicon rectifier for a long time is part of Infineon. So with that, we have been, let's say, a long time in this research, and now we are heading to, let's say, commercialize this technology with, let's say, with the focus on in the niche area. And then is the silicon carbide. In fact, the research of silicon carbide goes long back, decades back. And that's why this technology is definitely has come to the market before the GaN. The advantage of silicon carbide over silicon is that it offer, let's say, tens of hertz. And of course, the power in the range of, let's say, more than 1 megawatt, if not tens of megawatt. So this is one area where, let's say, power semiconductor R&D next 10 year going to take place. And definitely, as I mentioned, that this is a long R&D, and now is the time to get it commercialized. And the real push is mainly coming from the performance, where you have to deal with the battery. So, for example, X kind of electrical vehicle. So X, you can put anything, whether it is plug-in hybrid or it is range extended. And ultimately, the direction is towards the battery-operated vehicle. So over there, basically, you have to use available power in a very efficient way to avoid any kind of losses. And then the voltage requirement basically is going beyond the traditional battery of 24 volt in the direction of 40 volt and even higher. So silicon carbide is already making its way to electrical vehicles. And when we are talking about GaN, so this is also going to make a space into more energy efficient require where the power switching frequency requirement is higher. And so this would be, let's say, one area. The another area is definitely in terms of, let's say, more sense and control to connect the digital world to the real world. So there has to be sense. So Infineon is also focusing on in this arena, and definitely, for example, in certain area like silicon microphone, we are a very clear leader. And we have already launched a silicon microphone which offer you signal to noise ratio more than which was considered few years back like a red brick wall or roadblock of 70 dB. But Infineon, the latest silicon microphone, offer beyond 68 up to 75 dB. So in addition to that, there are discussion about integrating a lot of sensors. So it will also happen in the sensor arena where you can also combine a lot of sensor and a lot of research going on further in that area. The other research is mainly driven by autonomous vehicle, where you need to also provide some sort of sense to car. So for example, like radars and LIDAR and some other sensors. And whole sensor is already there are in the cars. Then there are R&D in magnetoresonance kind of magnetic sensors or giant magnetoresonance sensor. So these are few of the area which we will also see, let's say, find its way to the mainstream applications which are present at the moment, like as a little brother of silicon. So Preet, I pass to you now.
Okay, thanks, Dr. Raj Kumar, for giving your thoughts on the cutting edge research which is going on in general in the industry, and a quite focused domain for your organization. So with this, I'll move to Dr. Thomas. So I would request admin to bring up his couple of files, and quick time check. We are about, almost midway. So yes, Dr. Thomas, up to you.
Thank you. So first, I'd like to thank Professor for inviting me, and I'm very pleased to share with you views about mostly scaling. So I work at CL, which is the thing you with is working on.
Dr. Thomas, we lost your audio. We are not able to hear you properly.
You
okay. No, it's still the same. Looks like there's some bandwidth issue. Probably, yeah. Go ahead, please.
Can you hear me?
Yeah, we can hear you now. Yes, sir.
Yeah, it's better. I changed my network. Maybe it's better like this. Okay. Next slide, please. So this is a view of the Siemens roadmap with some of our anticipation on also. So as you know, today FinFET is the mainstream. So you mostly have two trends in the roadmap. The main trend is 3D with FinFET, and we'll see after gate-all-around and stack nanowire. And the second trend is 2D. With FD-SOI down to maybe 10 nanometer, it can still get down, and then there's some researchers also on 2D materials would be also a sort of 2D solution, probably limited by some electrostatics or fringing fields, and that will have to go to 1D. So the equivalent in 1D of 2D material is carbon nanotube or this kind of things. And we'll probably have to stack also for current drivability if we talk about the 1 nanometer node. So, of course, today most of the process is done in FinFET, and the process is ready for 5 nanometer and it's developing for 3 nanometer, and there's also some interrogation how to make the 1 nanometer. I think it's also one of the questions for this panel. So next slide, please. So this is also a vision from Professor Mitra, from Stanford, showing how the 3D can be, and very high dense 3D is the next, I would say, scaling possibility, as it was said in the invited talk before. The Flash 3D is entering in the memory, especially for the Flash, which is in the product today. And this very high dense 3D will continue probably with for interfacing the processing and the memory, or different memory level or different kind of memory also, with different material and principles. Next slide, please. So this is also an illustration about the end of the roadmap for silicon with the stacked structure. So at Leti, we have more than 15 years of innovation on those kind of structure. We proposed the first stacked nanowire in 2006, and then this technology developed. Recently at the last VLSI, we showed that we can go up to 6 level stacked nanowire, showing this technology so can continue to increase the current, because as you know, when you scale down the transistor for the FinFET, for instance, you have to also increase the height or increase the drivability of the FinFET. And it's the same for the nanowire. You have to add a nanowire on top of the other to increase the current drivability, and that's also a big challenge for technology, and the control of this process is a very big challenge. But many big companies and research labs show that there's some possibility there. And also I would say that this stack nanowire, it's much more scalable. So please, next slide, please. So if you consider the short channel effects, and in particular the dipole, and you compare nanowire with gate-all-around compared to FinFET, you see that you have more, that you can double the scalability, and even more than double the scalability. And this is why for below 3 nanometer, 1 nanometer, you have to switch to this nanowire structure. And the next slide, please. And the second point, once you have this, is to preserve the drivability, and that's why it's very difficult. But you have to increase and stack more and more nanowire on top of the other, and it's even more difficult, of course, if the technology is scaled down. Next slide, please. So another point is that for design you need flexibility, because having a low power device with good control of short channel effect is not enough. You need some current, or to increase your driving current for some part of your design for higher performances, and that's why in the current plan, the nanowire is also co-developed with nanosheet, which is a larger nanowire. So by your design and mask optimization, you can obtain both nanowire and nanosheet, which is large nanowire, but with higher drivability on the same wafers. And we have all this compromise between electrostatic, current, capacitances, because this 3D structure have a lot of parasitic capacitances to be integrated, and probably the design has to adapt, and locally you will have a different flavor of transistor. Next slide, please. Of course, about 3D, as you know, today you have a 3D, a very high dense 3D in your pocket for the flash memories. And the question is, you have up to maybe 100 level today in industry. And the question is, will we switch in this kind of very high dense 3D for logic or computing, which is more difficult, because of course the design is not a matrix design. This is the most difficult point for me. Next slide, please. And this is also an example of our recent results. We have from conclusion, showing how you can introduce this very high dense 3D architecture. The idea after the scaling of transistor is to mix transistor and memory in a very dense way. And this is needed for two applications. The first one is AI. So it was said by Professor Sharma, I think, that AI is the next driving point for those technology. So you can mix in 2D. We have a stacked transistor monolithically integrated in the first figure. And RM, which is used for a neural network for synapse. And the second point is in-memory computing, where you make some basic operation within the memory to accelerate this problem of memory bandwidth. And we propose also recently to integrate stack nanowire with resistive memories and we made basic operation on that. So it's like a memory matrix, a 3D matrix, and we can do some basic operation within this matrix. Next slide, please. Maybe it's the last one, right?
Yeah, thank you.
Yeah.
Thanks, Dr. Thomas, for sharing your views. So a quick summary, as Professor Dinesh said, technology, device structure, or architects, design style, or application. What would define, how next generation of chips would be done. Dr. Raj summarized on the high power, 6,500 watts or beyond with hundreds of amperes. How we can have some technologies using GaN, who can sustain with all such high power specialized chips or, chips related to sensors. And Dr. Thomas, you brought up this good perspective, it's 1D, 2D, 3D, nanowires, or, we are talking about gate all around technologies. So with this all, I would say diversified, angles. Let me kick on a few of the questions because it was hard me to, hold back me, having you all here to, talk about these questions. So my first question would be, is it possible to develop a technology sub 1 nanometer within next 1 decade? Anyone would like to take a quick pick on this? Any thoughts from the panel? Dr. Raj Kumar, you're on mute.
Thanks, Preet. Yeah, I was on mute. So let me give very quickly my 2 cents. So let's look pragmatically. The traditional way of let's say scaling semiconductor have been on which the semiconductor technology or the Moore law have been riding is the lithography in combination with patterning techniques like etching. So at the moment, basically the best way of doing under the blue sky is 35 nanometer based extreme UV imaging technology. And with the currently the optical numerical aperture of 0.33, that's the best what we have. And by 2023 and 2024, this numerical aperture can go up to, let's say, value of 0.5. But that's at the moment is foreseen as, let's say, the best can do. So thereafter, there's no cost-effective technology is available. Yes, it's possible, but in order to mass manufacturing something in a scale of semiconductor industry, what we have as in today, so the physical dimensions will be, let's say, limiting somewhere in the range of 6 to 7 nanometers. So this number also match with Professor Sharma. And the 6 to 7 nanometer as in today is projected somewhere around 2030. And now you're talking about, let's say, 1 nanometer beyond that. So I would say that the way to improve the performance is not only, let's say, reducing the dimension or going into the range of 1 nanometer where we are putting maybe 2.5 atoms together. Even it is possible, this might not be viable. So that's what my view is. But on the other hand, we can never underestimate research. So miracles are always possible.
Great, Dr. Rajkar. Thanks for putting your perspective. So, Dr. Dinesh, Professor Dinesh, Dr. Thomas, would you like to add up your thoughts on this?
Let Dr. Ernst come in.
Okay. Okay, I can add some few arguments. So, of course, I agree that we reached some limit, but for all my career in this field, when it was already said that we reached the limit, so maybe more than 20 years ago. So of course, there's also the limit of atom, that's the physical limit. But it was one of the arguments 20 years ago also. So physical limits, of course, I agree. It's very difficult to go below 5 or 6 nanometer because we have a lot of quantum effect, which are which are very difficult in terms of both variability, transport, and so the performance will degrade probably below this 5-6 nanometer. This can correspond for the diameter for a nanowire, for instance, you know. But technology finds always path, and there's not only the limit is not only the active device, but also the interconnection. How to make very high dense interconnection to continue to scale down the whole design, and we've seen in the past that the active device does not always scale down from one node to the other. Sometimes it's the back end, or sometimes the front end, and both. So also the 3D, I think. I agree with that. We will reach probably to an end, but the mix. I think the 3D and mix between memory and active transistor will continue. We make able to continue really the performance increase dramatically.
Oh, great. Thank you. Thanks, Dr. Thomas. Professor Dinesh.
Yeah, so I alluded to it. By the way, I had some network problem during my presentation. I don't know how much of it went through, but I referred to, climbing a mountain simply because it is there. Now, therefore, in terms of possibility, it is possible to reduce the channel length to any extent. I think we have always been proved wrong, and that has been a pleasant surprise. But the question is why, and do the applications on the horizon immediately demand that? And to my mind, rather than a brute force reduction in channel length, 3D integration and in-memory processing offers a much better fit to the kind of applications that we see coming over the next 5-10 years. Remember, these solutions are very expensive, and these solutions, even if they exist, will become practical only if applications demand them. And therefore, the technology is driven not just by possibility, but also by the need push from the applications. So to me, it appears that the immediate development is likely to be 3D and in-memory processing.
Excellent, sir. So there's a good perspective, and it's like the application drives the technology, okay? And if your use is a simple Outlook, then you don't need the best machines. Whereas if you're a gaming person, probably you would be looking for it. At the same time, it's like using a plane to go to office when you're in the same city. So yeah, so certainly we have a better, I would say, more efficient or more economical viable means available. But the world is always curious, when we were talking about 28, we said, oh, it's coming to end. Then 16, 14, 12, 10, 8, 7, 5 nanometer, and there are already announcement of 2 nanometer and whatnot. So now this brings, let me try to put in a little more flavor to the discussion. So what is the alternate to CMOS? Okay, so we have huge literature available, since our bachelor's or engineering days, reading about CMOS or discussing about CMOS with a lot of, publications all around. So what will be the mainstream you see with this, lower node technologies? They have their own challenges. So any thoughts, what could be the nearest or closest possible replacement for silicon, which can give us the same kind of, beauties which we are presently getting from silicon, all these years? So any thoughts?
If I may come in?
Yeah, yes, sir.
Yeah, so I think new technologies have essentially a tall wall to climb. The problem for that is because of the amount of investment currently in the CMOS technology. A new technology always has teething troubles, and people are impatient for performance. So we have seen various things come up and vanish. Recall the VMOS and many other things. So in the short term, I don't see a complete replacement of CMOS, but maybe in specific applications. For example, one is already seeing nanoments for power switching. So for specific applications, new technologies will start coming in. And once we have a nice collection of proven technologies available in concert with silicon, that we can think of completely new technology. But in the short run, I don't see a new technology coming and totally replacing CMOS like CMOS did to TTL.
Oh, great. Any thoughts you want to talk about, Dr. Raj Kumar or Dr. Thomas, on this?
I think there's plenty of new devices that enter, for instance, for the memory, and the fact that memory will work closer to logic. It was said about in memory computing or neuromorphic, etc. We make the limit very fade. Will fade the limit between, I think, the CMOS and the memory. And can you hear me?
Yeah, Dr. Thomas, we are losing you in between. I would request if you can try turning off your video, yeah. Probably the audio would improve. Yep. You there? Dr. Thomas? Okay, so let me meanwhile move to Dr. Raj Kumar. Dr. Raj Kumar, do you have anything to supplement the thought shared by Professor Dinesh and Dr. Thomas?
Yeah, sure, Preet. So as I mentioned that, although the question is basically, is there a life after CMOS and what would be beyond that? But as I mentioned that, the semiconductor is not only CMOS, there's also power world, and somebody doing the power semiconductors could be also in top 10 semiconductor companies. There's a huge R&D going into the power world. Let's say, as I mentioned, the silicon carbide has already started making the way. And if you look as on today, we have roughly, I would say that more than 150 product in the market, which is basically on silicon carbide base. And we are selling to, the 60 different customers. And GaN has also started making it way. So basically, there would be alternative to the silicon. And now let's go to the CMOS. So although I'm not actively involved in this arena, but out of my technical curiosity and being a senior member of IEEE, I'm also associated, with, let's say, a lot of discussions and what going to be the last after CMOS. So I see there are three candidates, on the very broad category level. So first one is, and which is going to be, I would say that more natural choice, and I will come to that why. So there are basically different kind of field effect transistors. So like tunneling field effect of transistor, either 3-5 semiconductor or heterojunctions, which we call like charge-based devices. Then there are electrical dipole-based devices, which is we also call like ferrum-based field effect transistors, and then orbital state. So this is one category which is we call like FETs or tunneling or dipole or orbital field effect transistors. The second category is the so-called spin devices, which are more or less magnetics. And of course, third one is always, let's say, discussed in different contexts is carbon nanotube and graphene and, graphene nanoribbon and things like that. But look on pragmatically. So how much, let's say, infrastructure and investment has gone in the existing semiconductor industry, what we have. So I'm talking about the front end part where the chip are really made. So from my point of view, the semiconductor industry historically have been an evolutionary industry. You know that you go from one node to another node. If you wanted to introduce a material like copper, you need decades of R&D and at least 10 years of development. And then you look like EUV, which also need actually at least 20 years of development to get into the mainstream. So looking at the historical progression of semiconductor industry, I think the best way to transition from CMOS to the next would be some sort of, let's say, field effect transistor. And this tunnel field effect transistor and heterojunction field effect transistor, I mean, both are tunneling based. I think that's make a little bit viable candidate. The reason being is that it's not like a revolution that you have a lot of infrastructure and tomorrow you can create something else. The second reason is that look into electrical property, and if you look into sub-threshold swing, the heterojunction I think can offer you better than let's say 60 millivolt and better. But whereas for rest of the things at the moment, I think a little bit more R&D will be required.
Great, Dr. Raj Kumar, putting together your thoughts here. So I just want to put a similar corollary example here. So we all used to turn over TVs with hands before the remote set came in. And now if you are not able to find out remote, you go and look for a remote. You don't walk into TV to turn it on. So that's how the technologies are. Once we are savvy of one technology, we prefer to, look around, but at the same time, the commercialization decides, what becomes big. As a researcher, we have a lot of avenues, and these researches are happening across the globe. So let me bring it to a closer question. So now I'm not talking about particularly CMOS. I'm talking about, how feasible is to have multiple technologies manufactured on the same wafer, now with logic, DRAM, NVM, sensors, etc., and whatnot. So any insights about this particular aspect?
Yes, maybe I can comment. Again, I keep the same view about integrating for instance, back-end memory for a microcontroller. We integrated 5-change memory, and so 5-change materials. MRAM also is entering in the backend. So those kind of new technology, RRAM also, many kind of RRAM, they are all backend compatible, so we can do them at low temperature without while keeping the performance of the CMOS below. And so on the paper, it's quite possible to co-integrate these different kind of materials and memory, and it's very interesting because, of course, as a memory, for instance, they have a different property. Some have very good endurance, like MRAM. Others have very low power, etc., etc. And for future system, and some material, it was shown by Intel, for instance, that you can use spintronic also for computing with some specific architecture. So using those magnetic material. So we can imagine in the future that we combine those material on the same chip. Of course, the application is thriving and the cost will increase if we make the technology more complex. So, of course, there will be a compromise to do there about the complexity and the costs. And
Certainly. So on the research perspective, I would still call it, a lot of initiatives are happening. But Dr. Raj Kumar, do you see, such technologies getting commercialized in the times to come, where we have, more than one kind of, integration happening on the same piece of paper?
Yeah, sure, Preet. I think there's already product available in the market where some kind of thing can be combined. That we have the sensors and CMOS together, then this 2.5D already bringing, that memory and logic together, and 3D will also bring more. But again, I think Professor Sharma has said rightly, I mean, there's no point of going to a mountain just for the sake of going over there. So technically it's possible, but the question is that why you wanted to do it. At the end, you are looking for the performance, you are looking for the cost per performance, and then you're also looking for, that like a solution which basically is reliable for the long term, and then it is also let's say easier to do, instead of, let's say, doing the difficult thing and finally have the low yield. So I think somebody was also talking about the yield. So when you try to combine a lot of things together, the yield is another factor, so you cannot optimize together. So sorry, Ernst, I have to speak one sentence in Hindi. हमारे यहाँ एक मुहावरा होता है कि कहीं का ईंट कहीं का रोड़ा, भानुमति ने कुंबा जोड़ा. So basically, if you like to integrate the things together, then the situation is going to be happen like that. So there would be certain things which can be combined, they will be combined. There would be certain things which can be combined but doesn't make sense.
Exactly. So as I mentioned, from research perspective, you can prove on the research, you can prove on the facts, but how well it will see, market for tomorrow is something very, more application driven. Oh, that's excellent. We are, just hitting the time, but I just don't want to hold back with this one of the question which came from the audience, and which I also am curious about, and I was talking to one of my friends from EDA. So they said initially it was more of the devices, and there was some part of interconnect sitting. Okay, we were more worried about the device part. Okay, but somehow gradually what has happened is, as the technology shrunk, we say device fine, we are still able to take care, but this massive interconnect is really troubling me a lot. The mathematics is becoming more and more difficult to solve, and our major compute, or I would say major focus is getting diverted to see all the troublesome coming from all of the interconnects. So do you see in long term, what is your opinion, will interconnect scale at the same pace or give us the same kind of performance as we hit down? I'm not talking about 1 nanometer or sub 1 nanometer, but what is your thoughts on the interconnect sides of the technologies?
Yeah, so may I come in?
Sure, sir.
Yeah, so it has been and will be a big bottleneck. However, our ingenuity in design often steps around such obstacles, and I hinted it in one of my slides that you choose architectures which don't use so much global interconnect and rely much more on local interconnect. Some clusters of PNNs and so on. And I keep repeating this, that perhaps for the next decade, we will not have one killer technology. We will have application-specific technologies as well.
Dr. Sharma, I think we lost you. Okay. Meanwhile, I'll move to Dr. Thomas or Dr. Raj Kumar about your thoughts here.
Yes, I agree. Interconnect would have to find. I think there's breakthrough to do at interconnect level as much as at the active device level. In terms of course, the kind of dielectric, the kind of also metals you want to enter in very thin interconnect, and then maybe find engineering ways to to go around the physical limits as we've done in the past, right?
Any thoughts here, Dr. Raj Kumar?
Yeah, Preet, I share the same view. Actually, interconnect is already hitting a wall. And if we have to, let's say, scale interconnect, then it has to go beyond the traditional methods, So we have to go maybe to something else, maybe nanowire, carbon nanotube, which offer the smaller dimension, but still very high current capability. So that would be the reason, but I'm in the power semiconductor, but let me tell you here, so silicon offer actually much more capabilities, really getting difficult to get current out of the device. And that's why, that like copper and some other composite, which is first made its way because of the RC combination in advanced logic, but now they are also part of the power devices, and not because of it is the smaller dimension what we need. Actually, we have big metal pads, but they are needed over there to really get out the current out of the silicon and maybe gallium nitride and silicon carbide. So I would say that at least it's really getting a metal R&D instead of semiconductor R&D from my perspective.
Exactly. We were talking about gold, aluminium, and copper. So there are some cost and there are some characteristic both involved. So this is, I don't really want to stop up here, but we need to, see the ringing bell of the time. So I would like to get to a conclusion because Dr. Raj Kumar, you mentioned about, the materials like silicon carbide, GaN, and sensors, etc. So I would request, if you can briefly, quickly help us out to, make a hit about GaN, silicon carbide, and the traditional silicon-based CMOS devices. Concluding remarks from you.
Yeah, so Preet, as I mentioned that we already have product in the market. The real topic is basically, how we can reduce the cost, how we can further improve the reliability, because these are the devices which are making the first time. And still there are certain topics which has to be resolved, like silicon carbide, the biggest substrate is 6-inch. So one of the way, apart from scaling semiconductor industry, let's say, progressed was the wafer size. So sure, I mean, silicon carbide still have way to go to 200 mm and eventually maybe one day 300 mm. Apart from the reliability, then cost will also come down. Then of course the mass production will also need to get into. So sometimes the chicken egg type of equation, they will be resolved by the time. Then GaN is definitely the new candidate as compared to silicon carbide. So the similar topic over here. So here approach is different. So substrate size are available because you are using GaN on silicon. But there's also still challenge to do the FE and then do it defectless and do it at the price of silicon, for example. And then comes to the MEMS. So MEMS is basically relatively new. They are not electrical device. They are rather electromechanical devices, and sometimes they also go into biological domain and stuff like that. So there are a lot of possibilities over there in terms of improving the performance, in terms of system integration, in terms of improving a different kind of figure of merit. So yes, I'm not really worried about whether 1 nanometer is possible or not. But what I say is there are a lot of possibilities. There are a lot of space on the top. There are a lot of space on the left. There are a lot of space on the right. And of course, there are also still some space on the bottom. That's my concluding words.
Great thoughts. And as you said, we need to look around 360. It's not only the one direction the focus should go, but we need to see how we can have more commercialized, low cost, high performing devices coming in, rather than only just talking about, okay, it's 1.5 or what next. So with this, I would move to Professor Dinesh. You started the discussion with a really thought about, technology, device structure, design style, and applications. So any concluding remarks from Professor Dinesh for this discussion today?
Actually, I'm very happy to have been here and hear very well-informed views. It does appear to me that some devices are really promising, as Dr. Ernst said. For example, one-dimensional devices, gate-around kind of things, combined perhaps with carbon nanotubes. So the potential still exists. And I essentially maintain that whatever comes to the fore will be driven by what is needed by the applications. And if one looks in the short term, then the applications appear to be automobile, machine learning, and so on. So one has to look at the kind of immediate requirements that are posed by these applications and see what is the best fit to those applications. And there will be roadblocks. You mentioned interconnects. I have worked for long on interconnects. That is a difficulty, but the ingenuity of design is to step around difficulties and come up with a solution which is practical in spite of the difficulty.
Thank you. Thanks, Professor Dinesh, for sharing your views. And it's not about the only the devices. It's not about only the interconnect. The whole the whole system. Devices with interconnect has to work seamlessly as you move across the materials or across the technologies. With this, I would move to Dr. Thomas to share his concluding remarks before we call off this panel for the day.
Okay, thank you. So I have two interesting points that I would like to enlighten there. The first one is that for me, AI, and I agree on that point, AI, I think embedded AI will drive the last nodes. And for this embedded AI, you need power, computing power. And you need also memory, embedded memories, and this will drive. I think this is a big market, and I completely agree on that point. And the second point is maybe the limit between more and more than more is shedding more and more, because you have this embedded power of computation that you find now in advanced sensor, advanced imager, maybe in the future in power devices, but at least in automotive and MCU. And we have really to think differently and do not separate any more and more than more, I think.
Great. Thank you, Dr. Thomas. So let me briefly summarize. We already hit the time well. I would say quite decently. We accepted this slot, but this was so exciting discussion, and it's a big honor for me to be part of this. So a quick summary here is like the research. Research drives the technologies. There are different aspects which we get into, but the applications would define what would be commercialized or more viably going to be tomorrow's technology, like AI, in-memory computation, things like electric vehicles, automotive or autonomous altogether. Okay, but at the same time we'll have our own challenges, be it the shrinkage on the technology node, be it different materials available, be it combination of all these materials at a single piece of wafer. So with this, I would conclude this panel with a big thanks to each one of you. At the same time, my apologies that Dr. Satya was not able to make it. As I mentioned, due to immediate demise in the family, may his family members' soul rest in peace. So with this, we'll conclude this panel. I have a small token of thanks, a virtual token of thanks for each one of you here. Admin, could you please bring up the slide? So thank you so much, Professor Dinesh, Dr. Raj Kumar, and Dr. Thomas, being part of our this exciting panel discussion, and we are looking forward to continuous, representation by you in the upcoming similar aspects related to VLSI Society of India. With this, thank you so much again.
Yeah, thanks. Thank you very much.
Thank you. Yeah.
Thank you. So by this, we'll conclude our today's this session 0. We'll break into the parallel sessions for rest of the day. We'll have session 1A, 2A, 2B, 2-3 going on in the respective parallel sessions. So I would request audience to go and join and enjoy those sessions. Thanks a lot. Have a great evening, and I'll see you guys tomorrow. Bye-bye.
Bye.